Okay, so can you see the screen I just shared in Zoom? Okay, good. Okay, so today it's lab 8. So go to modules, and there is a week 11, and there's a lab 8. You need to download the HTML file, and then also we have two CSV files, credit data and serials. So we're gonna make a neural network model with the two data sets for this lab. And then, of course, I'll open the R studio, then make a RMD file, right? Good. And then set up the repository like this way. So we have RMD file in this repository, and then with the same repository, you need to make a data folder. Whatever name you need, you can just make up the name and then put the data inside. Sure, it's error as well. The one package. Yeah. So you might need to exclude this package to meet the. So we run it for all. Actually, yes. So I said just copy some part of the block, copy the other part of the block. This will make it larger. Then if there's an error, then you can find where the issues. Or make it come. Oh yeah, run all, but I don't really work. You can just lock. Okay, good. So before we go to neural network, I think you already took the class about neural network last week, I guess, from Simon Brewer. Let me briefly explain what neural network is, right? So here, if you Google neural network, we always start studying with Google sometimes. So just type neural network in Google, then you can find this type of machine learning process called deep learning that uses interconnected nodes or neurons in a layered structure that resembles the human brain. Right? So it follows the structure of the human brain. It's just, but if you find the image of neural network, there should be the picture of this. So you can see here you have three types of layers in neural network. Sorry. Thank you. So first one is the input layer. So input layer is the same as the input features. Okay, so each node here represents each x1 and x2. So it's like an independent variable, right? Features. And also there's a 1 plus 1 node here, which is called the bias feature. I can explain later. And then also second layer is called the hidden layer. So actually number of hidden layers are decided by you. So it's like a hyperparameter, right? And then a third one is output layer. And then output layer should make the result, make the outcome of this model. And then also there's one more, actually we call it sometimes layer, but one more thing on the far right is called loss function, right? So loss function should be here to determine how much error occurs, to show how much error occurs. So we have 3 layers and 1 loss function here. Okay, so this is the basic structure of the neural network. So I think you all heard about I think you all know the regression analysis, right? So I'm gonna give a brief example of how neural network works with the regression analysis, right? So here is the structure of the neural network. So we have first input layer here, and the second layer here, and the output layer here, and then there should be a loss function here. All right, so we have these 3 layers and 1 loss function here, right? And then we have here, so first layer, the input layer has 2 features, x1 and x2, right? And then we have 1 bias features as 1, numerical value 1, right? And then also z1 and z2 in the hidden layer. So z1 and z2 will be the output of the first input layer. So I'm gonna show you how it works. And then also we have output layer as y. Okay, we call the output layer as y, right? So y is the ultimate output, right, of this model. And then we need to define the model first. So in hidden layer, we define the model as a sigmoid function. So the output of the second layer will be sigmoid. So sigmoid is, you use a sigmoid function, the sigmoid curve also, for the classification methods. So for example, like if the sigmoid curve value is more than 0.5, then you decide this the output as positive, right? And then if it's below the 0.5, the output will be negative, right? So it's a classification. You use the sigmoid curve, the classification method. So we decide the sigmoid activations in second layer, and then the third, like ultimate output, we set the linear activation. So the ultimate the results, the outcome of this neural network will be the result of a linear regression. So it will be the numerical value, right? So second layer, the result will be plus or minus, right? Decided by sigmoid curve. And then the output layer will be the numerical value, right? So in this situation, we can make a weight. So the weight here is a really important concept in neural network. So weights are assigned to each link, that links the nodes, right, between the nodes. So here we have a W01 because you can number this node from 0, 1, 2 in first layer, and then 0, 1, 2 in the second layer 2, and then number 1 here. So the name of this W is W01. Of course, this will be the W22 because it links the X2 to Z2, right? So we name the weight like this way, and then this weight will play a role of making the better performance of the model. So for example, let's start from the first node, and let's start from Z1. So we decide, we make the model of Z1 first, using the all features first. All right, this is the first step of neural network. So we make a model of Z1 named Z1. So Z1 is the model, but also the outcome of this model. So here, delta is a sigmoid expression because we set up the model, the sigmoid model, right? So, and just ignore it. You only think about here. So this is the model that we first make with the neural network. So here we have a W01, right? So W01 is this weight, right? Multiplied by 1, right? That's why this becomes a constant variable. And then X1 multiplied by W11, right? So here is the model. And then also W21 multiplied by X2, and then add up everything. So it looks like linear regression model, right? It totally looks like a regression model. So we made a regression model named Z1 first, right? This is the first step. And of course, we need Z2 linear regression model too, right? This is the second model, right? All right, so now we made the two models with the first layer, right? And then with the second layer, we made the output, right? So that is the next step. So for the next step, we made a Y model, right? This is the ultimate output. So we use the output of the previous step, which is Z1 and Z2, right? To make a regression model, right? Make a Y. So this is the basic concept of linear regression. I mean, the neural network. So first, with the first layer, we made two models, right? As the same number as the second node, right? And then using those outputs, we make a one ultimate model, right? So and then output will be Y, which is the output of linear regression, right? And then so this is called forward pass, all right? Forward pass, and then we use a Y. We made a Y right now, but here there's no clue, right, to make a W, right? W because W is all W are assigned by randomly, right? So first step, the result will be really poor, right? Really bad, right? So first forward pass, we also call the first iteration. The result will be really bad, but there should be a loss function. I'm sorry that this slide doesn't have those concepts, but there should be loss function. So loss function measure the error and then give a penalty if there's too much error. And if there's too much error, then this loss function propagate the error back, through the network, so that the W here, like all W, will be adjusted in the next step. And then forward pass again to make a better result, right? So this is called the backpropagation, all right? So neural network, we keep doing forward pass and the backpropagation, right? Again and again to make a better weight, right? And then better outputs. So this is like a basic process of the neural network, right? Okay. Yeah. So any question about neural network? Is very brief. Very brief concept.
So the loss function, it just like, does it find like the derivative? Is that, I don't remember from that.
Yeah. So actually, the loss function main like a role is to give a penalty. So like this. So I'm gonna show you the loss function. So yeah, derivative is like a coefficient, right? It's the same as weight, right? So loss function actually play a role as adjusting the derivative, but here this is loss function. Is
Right.
So if it's a zero means it's a accuracy. It's really good, right? But if the error comes, like one is like small error, but two is large error, then it counts everything, and then it measures the error with this the graph, which is based on the type of depends on the type of the loss function, and then you penalty to do the backpropagation to mitigate this error, right? Yeah. So this is just that's a loss function. Okay. Yeah, this is good. Picture, I guess. The loss function find the derivative will be the difference between the prediction and the observation, then measure the error, then make the clue for backpropagation. Okay. Any question about network? Because this concept of backpropagation iterations, you need to memorize those two concepts to run the model for today. Right?
So does it like when it's checking the parameters or the weights, does it try like on either side to see if whether the loss gets better or worse? Does it like?
So you mean the both sides?
Like does it like if weight one was like, 1, would it try like 0.9 and 1.1 to like see which direction it went? When you're trying to like optimize the weight?
Yeah, so you mean if you ask for the direction, and then the number, I mean.
Like, how does it find the optimal?
Oh,
weight?
yeah. So actually that is quite complex.
Okay.
But you know, you use the yeah, so you said the derivative, right? Right. Well, you know, I think I'll give you the another PDF. Right? This
Okay.
explains really well.
Yeah.
So I'm going to show you. So because that is actually a little bit complex.
Right.
Yeah. And
you would have
yeah.
to make it another separate like model, wouldn't it? For like the.
Yeah.
Yeah.
I mean, yeah. The more node, yeah. That's really yeah. But anyway, yeah. I'm going to give you the PDF, or maybe we have time on the next slide. Yeah. So. All right. Let's open the HTML5 first. Right. Right. I assume that everyone download the data right now, right? And set up the all, you know, the RMD file like this. So let's start from the first line. Introduction. So we will go over 2 neural network examples with the 2 data, right? 2 data sets. And then there are simple 1 or 2 hidden layer networks, but we're gonna use just 1 hidden layer to make a model. And then we build the model and also tune the hyperparameters for the network. All right. Okay. So please, you know, download or install the packages or import the library, the 2 libraries here, BPLYR and class reverse. So there are lots of packages that enable you to run the neural network. MLR3 is one of them, and it gives a really simple code to run this NN. So I call the neural network as NN from that. Okay, so and then okay, let's just run the simple linear regression first to track the relationship between the x and y in this data. So please, you know, read the serials.csv file, right? Please load the serial.csv file to your RMD. And if you print the head of the data, and you can see there's a name of the serial, right? And then some type and how much calories is inside, and the protein, fat, sodium, and so on, right? And there is like a last column named rating. So it's the result of the rate. So we will gonna predict the point of rating. Okay, so with the other columns. Okay, and then we only use these 1, 2, 3, 4, 5, 6 columns to make a task data. So the last 5 columns will be the features. The first column, which is rating here, will be the targets. All right. Good. And then just load it GLI to to draw the graphic here. So let's just draw the correlation plot here to check the relationship between those x and y. So here the rating point shows like a negative association with the calories and fat and sodium. And then the positive relationship with proteins and fiber, right? Okay. So it means that the more fat, the more sodium, the more calories, the less rating this cereal gap. Okay. And then if you plot the histogram with this code, you can see the histogram of the rating column, which shows the normal distribution. It's almost a bell shape, so we don't have to adjust this column and this value and convert this to maybe log or not. So we don't have to put the log on it because it already shows the normal distribution, right? Okay. And any questions before going to next step? Okay. All right. So before that, we need to rescale the features, right, with the min-max scaling. This is one of the normalization method. So here, because calories and protein, fat, sodium, and fiber, has a different scale or a different unit, right? So we need to make it, same. Make the unit same. So we run the min-max scaling method to make all the columns range from 0 to 1, right? Right. So you can define, you can extract the max values and min value of each columns, and then execute the min-max scaling, and then put the min-max scaled features and also the rating columns into the same data frame, which is called the scaled data. Okay. So now we made the scaled data that we're gonna use this scaled data to run any models. Okay. So now if you print the scale data, then you can see, all right, we have 6 columns. The first rating columns will be the targets again. And then all 5 columns is now has the same scale right now, right? From 0 to 1. Right? So with this data, we're gonna run the linear regression model. So to run the machine learning model, we always make task data first. Okay? So to make the task data, we use a task regression function here, and then make a new data, which is called the serial. This is just a name. And then the data we're going to use is scale data, and the target column will be the rating. Right? So let's make a serial task data first, and then set up the error measurement method to the RMSE, and then set up the 5-fold cross-validation. So with the 5-fold cross-validation, we're gonna ultimately we're gonna make 5 models, right? Good. And then we set the anti-learner as the linear regression model, and then run the model with the resampling function like this way, right? So just follow up this, and just copy the code to run the linear regression model. Right? Then there should be the 5 models we're going to be made, right? Right. So, have any question?
I read the next step.
Uh-huh.
And is there any reason why aggregate RMSE would be different?
Oh yeah, of course it should be different. Yeah, I see. So it should be different. Yeah, because you use different random seed. Yeah. Right. So this is linear regression because we use gradient descent function. So it means that we start from the random weight. So everyone's result will be a little bit different. Right.
It's like a figure of 5. Yeah.
Okay, so let's see my result. My result is a 6.4. Yeah, so 6.4, which is not very bad because the range of the rating is from 10 to 100. So 6.3 is not very bad. Yeah. But maybe we can make a better model with the neural network later. So, right. Okay, good. Any questions?
Yes. So because Sonnet is that exists several libraries, and then this find this find which library. So you need to look at this certain library or something like that. Specify the arm to use in API. That's weird.
Right. So now with a simple regression model, we have the error 6.34, right? So maybe we could make a better model with the neural network. So let's try with the same with the different model with the same data. So let's make the empty neural network, right? With the size of 3. So here the size is the number of the node in hidden layer, because the MLR3 packages only provides you to make a one hidden layer neural network. So there's no actually the hyper. I found it yesterday, but I found that the MLR3 package doesn't have those functions. So you could use a Keras if you want to make this complex neural network structure, right? So we make the size of we've set the size of the number of nodes, the hidden node, to 3, right? And then run the run the model with the same data, right? All right, and then let's just print out the RMSE. So that, all right, and then my result shows 10, right? So it's a worse, right? We now has the worst result than just simple linear regression, right? Because we didn't tune hyperparameters, right? Because the neural network starts from random weights, so it might be like a bad result if we didn't tune the hyperparameters and didn't run the enough number of iterations. Okay, so here we have, if you run the neural network, you can find this, the result that is printed out like this way, right? We have a 22 weights, right? So 22 weights, why is there a 22 weights? Because we have 5 features, right? And then plus 1 bias nodes, right? So we have 6 features, right? 6 nodes. And then in the first input layer, okay, I'm gonna just have this paint. So we have 22 weights, right? So we have 5 features in the first layer, right? And then also we have one hidden bias node here, right? And then we have 3 number of the node in hidden layer, and then 1 output, right? So this is our structure of the neural network we just made, right? And then here we have 1, 2, 3, 4, 5, 6 link, right, to the first node in the second layer, right? So we have a 6 multiply 3 weights, which is 18, between the first and second node, the second layer, right? And then we have a 3. But we also have a bias here, right? And then there should be 4. So plus 4, which is 22 weights. Okay, so that's why we have 22 weights to adjust. So, all right, so we have a 22 weights, and then the first trial we have like almost how much 126,000, right? MSE maybe. I don't know what error measurement this ML3 package uses, but I think it's an MSE. So, and then the first trial with the random weights, it shows a really bad result. But the second iteration, I mean, the 10th iteration, right, means that we already ran the 10th propagation, right? And then the result shows, 3,000, which is way better than the first iteration. And then getting better and better, like a gradient descent, until we reach the optimum, global optimum, right? So the error of this model becomes the difference between the error between the previous iteration and now iteration. Current iteration is slight and slight. So we just stop if the model doesn't show better, right? So it stopped after 100 iterations, and it shows the RMSE to 10, but it's bad, right? It's just worse than the simple linear regression, right? Okay, so now we adjust the size and max iteration to the 2 hyperparameters for neural network, right? So we set the size as 10 and set max iteration to 500, and then run the model again and see the aggregated RMSE, right? And then my result is a 15, which is the worst and worst, which is really bad result. So maybe the model is too complex to get a good result. So we need to tune the hyperparameters. Okay. So how to tune the neural network? It's just the same. We always tune the hyperparameters with the ML3 package prompt set function, right? So let's check the prompt set of the neural network. And then there's like a lot of hyperparameter sets, and then we will adjust tune the 3 hyperparameters. First one is size. Size is the number of the nodes in hidden layer, and then also max iteration, like how how many you'll run the backpropagation test for, right? And then distance decay. So because the neural network applied gradient descent, it follows the gradient descent concept. So there should be the decay as hyperparameters, right? So if the decay is too high, then the neural network result will gonna be like oscillated, right? It cannot and cannot reach the global optimum. But decay is too small, then the model will gonna be stopped before it reaches global optimum, right? So we have three hyperparameters to adjust, and then just set up the sampling method for sampling the hyperparameter from this range, and then what is that? Yeah, and for 20 iterations per model, right? Because it takes a too long time if you set up too many iterations. And then we use the three-fold cross-validation to run the model. So it makes three models, to last. So we make the tuner with those settings, right? And then run the model with the three-fold cross-validation settings, right? And then just print out the RMSE result. They're gonna take some time. If you run the model, then please check the RMSE and whether if the RMSE is slightly better than the previous simple linear model. Oh, so again, we use the RMSE outer. I mean, we set the cross validation for outer setting is to 5. So we made a 5 volts, right? So ultimately, we're gonna have a 5 models as a result. So I got the result of the 5 models outputs like this way. So we have 3 hyperparameters, right? And then the result corresponding to the 3 alpha parameters. So my result shows the 5th one. The 5th model shows a bad result, right? Your results were going to be different. You might have like the best model. Maybe it's the second one or third. It's really totally different. Okay, so my result shows that if we set up the size of the node to 2 and decay like this, and the next iteration to 50, then it shows a bad result. So I'm gonna use those hyperparameters to make the model. to make a prediction, right? So you might have the difference in result. You might have like this, that second model would be good, or third model would be good, right? So anyway, I'm gonna use this fifth, the hyperparameters result to predict the model, all right? Anyway, so let's make the ultimate model with the fifth hyperparameters, because my result shows that this one has shows good result, right? And then plot it. And if you plot it, then this shows the structure of the ultimate neural network I got. With the tuned hyperparameters, your results will gonna be different, right? Good. All right, so good. Is there any question? Okay. All right, so from now, until now we ran the neural network, and then the output, function was regression, right? That's why we got a numerical value, and then the set the measurement methodology as RMSE. If we use the classification method, then the results were gonna be like 0 or 1, right? So you should need to use a different measurement method. But here, so because we have a regression model, we use RMSE, but now we're gonna make the different model, just classification method with different data set. So the data set we're gonna use is credit data, the CISV, right? So it records the individual's credit score, and also their like some demographic values. All right. So let's load the credit data. All right. And you can see there is a status, right? So this column is the column that we will predict with the neural network, good or bad. So this is totally classification, right? So we're going to use a neural network classification model, right? Good. And then the process is all the same, right? We can just make a task data and then make an empty learner, and then also set up the hyperparameters, and then there are other like settings like how many folds for the cross validation and so on, and then run the model with the result. So I think you all know the process. I'm going to just skip, right? But before that, we need to pre-process data to convert the data to some some adequate the data scale. So if it is character data, we're going to convert this to the vector, just classification data, right? And then if the column is an integer, the value of this column is integer, then we convert this to numerical value, right? So we're going to make the columns have all the same scale, like this. Not scale, the data type. Sorry, yeah. So we convert the data type to the vector or to the numerical value, like this way, right? And omitted NA data, right? And then make the task data with this credit data. And also we set up the five-fold cross validation to make the five model, and then set the error measurement method to AUC score. And I explained this before, like in the previous lecture, so I'm going to skip it. And then set up the hyperparameter like this way and just run it. let's check the AUC. Of course, it's your choice to tune the hyperparameter, but in this lab here, in example, we don't tune the hyperparameters here. We can just put the, we just made up the hyperparameter like this, and then check the AUC score like this way. All right. So it shows the process of the. So far we ran the neural network regression and neural network classification with the two data. Then in this exercise, I think you need to provide our code as well. So so this is all for today. Please let me know if you have a question. I'm gonna be here till 1:05. Okay, thank you. And is there anybody in the Zoom with a question? Let's stop sharing.
Hello.
Yes, it's Muafa.
Yeah, I don't have question about the lab, but I wanted to book an office hour with you, but your office hours coincide with my class.
Oh, I know that. Maybe we can meet at 5 p.m. as we always did, right? We did before. 5
Yeah,
p.m.
5 Yeah, 5 p.m. That would be good.
Okay, 5 p.m. Yeah, just 5 p.m. So please, access the Zoom with this code, this address, right? This level.
Thank you.
All right. Yeah. See you in 5. Okay. I'm gonna stop recording.